Oh, hey girl, how's it going? Today we're going to go through question number 2 in this Level 2 2023 exam. We're going to be looking at structure and bonding. It's going to be very fun. The last video we went through question 1, so it was very fun. We did that. We got an excellence. It was great, so go back and watch that if you haven't done that. But today we're talking about question number 2. Okay, I'm very excited. I hope you guys are too. It's going to be great. Okay, question number 2. Ethanol is used as a fuel by reacting it with oxygen gas in a process called combustion. That makes sense. Okay. The combustion of gaseous ethanol is shown below. Okay. There it is. Looks great. What do we have? We've got ethanol plus some oxygen going to CO2 and water. Very awesome. Oh, that's how you delete. There we go. Okay, so what do we want to actually do? We want to use the change in enthalpy, which we're given right here, for the reaction above, and the bond energies listed in this table here, to calculate the average bond energy of the O double bond O bond. This one right here. Okay, so it is asking us to calculate that bond energy or bond enthalpy for this O double bond O bond. So like it would be nice if they could just give it to us here with the answer. But they didn't. Oh no, they left it off the table. That's just so silly of them. Okay, so let's go calculate it. Okay. So the first thing we need to do is look what we've got. We have the bond energies for all of the bonds except the oxygen one. And we've also got this delta RH, this change in enthalpy value up here. So there's probably an equation that'll like relate those two together, hopefully, yes. Yes, there is. Okay, let's have a look. So the change in enthalpy is equal to the sum, which you can write this fun little sum sign. That just means the sum. But we can write the fancy one just to be fancy. So the sum of the bonds broken minus the sum of the bonds formed. That's an S for bonds. Okay, beautiful. So we've got this equation that tells us the sum of the bond energies for the bonds that are broken minus the sum of the bond energies for the bonds that are formed equal the total delta RH value. Cool. Do we want to know like why this exists, or do we just blindly trust it because it's an equation that's given to us in NCEA? They love doing that. But so bonds broken, like it takes energy to break a bond, which sort of makes sense. Like there's this, C carbon bond right there. It's chilling, having a good time. You have to put some energy into it to break it. Makes a lot of sense. How much energy? 348 kilojoules per mole. Okay, makes beautiful sense. So that's energy going into the system. But when bonds are formed, they release energy out into the surroundings, which makes a little bit less sense, like intuitively, than bonds breaking. But if you think of it like a bond is just a real happy place for the atoms to be. Like look how happy. Look how happy this oxygen is. Look, yep, okay. So bonds are generally a state of low overall energy. So atoms want to be bonded. So if you think about like atoms on their own having a higher amount of energy, and then when they go and form a bond, the overall energy decreases. So they have to put their energy somewhere. It's not going to be destroyed. So the energy just goes out off into the surroundings. That's a relatively simplified way of why when you form bonds, it's going to release energy. You don't need to know that, but it's just for fun. That's what we're here for. We're here for fun, right? Chemistry, yes. Cool, so that's where this equation comes from, because it's the energy you're putting into the system, like the energy absorbed by the system, minus the energy that's like going out into the surroundings. Makes a lot of sense. Yes, it does. Okay, so now that we have this, it's just like plugging in some numbers, doing some math, and then working out the bond energy for the oxygen. Okay, should we do that? Yeah, sure, let's go. Okay, what do I want to start with? Let's start with the bonds that are formed. Okay, what do we form? CO2 and H2O. So if we look at CO2, this is formed right here. We have one C double bond O and another C double bond O. Okay, so we can write that. 2, lots of C double bond O's. Very good. Now, but they're here to trick us. Yes, they are. Because if you look back up at the equation, you can see under the CO2, there's this molar ratio of 2. So we can't forget about that. So you need to go back, have a look at the equation, and see that's in a 2 molar ratio. So therefore, we need to times this overall amount of C double bond O's by 2. So we get a total of 4 C double bond O. Okay. Then we can use the values provided, which is 805 for C double bond O. Okay, and we can just like do some math. So that's like 4 times 805. Let's just put units, because you know I love putting units in. Just generally units everywhere is a nice thing to do. Always include the units, even in the working. It helps you with things. Helps you not forget where you are and everything. Cool. So I'll put that into my calculator. So we get 3220 kilojoules per mole. Oh, that's an O. Yep. Okay, cool. So that's your CO2. Now we're up to the water. What do we got here? We've got one OH bond. We've got another OH bond. 2 OH bonds. 2 OH. Now, what do we do? Don't forget, look at the mole ratios. Look back at the equation. What do we have for H2O? Oh, we got 3 this time. Okay, so we need to times this by 3. That equals a total of 6 OH bonds we need to account for. Cool. Now we go back to the table. OH is 4, 6, 3. And let's just do that. So 6 OH bonds times 4, 6, 3 kilojoules per mole. And that is equal to, put this bad boy into my calculator. I brought the calculator this time and I didn't do the math. So it's like we're really doing it together. It's exciting. I'm having a great time. I hope everyone's having a great time following along, if you're still here. Okay, so that's 2778. Perfect. Okay, so that's everything in the products, right? Everything that's formed is here, and we've done that. So let's total it together. So we can just go 2778 kilojoules per mole plus your 3220 kilojoules per mole. Now, back into the calculator, and we get 5998 kilojoules per mole. So this is for the bonds that are formed. Okay, that's how much energy is released in this reaction per mole when they're formed. Okay, very good. So we got that. What do we do next? We need to do the things that are broken. Makes sense. Okay. Broken bonds. We're gonna run out of room here. Cool. So what's broken? We've got ethanol and we've got oxygen. Okay, let's have a look. Ethanol, what do we have? We've got one C-C bond. One C-C. And the nice thing is ethanol is in just 1 molar ratio, so we don't need to worry about times it by anything else. So that's just what it is. It's just 348. There she is, right there. Don't even forget units. I didn't forget anything. Okay, cool. What else we got? CH bonds. We've got 1, 2, 3, 4, 5. 5 C to H bonds. So we go 5 CH's, which is equal to 5 times CH, which is 413 kilojoules per mole, and that is, do some quick math, 5 times 413, 2065 kilojoules per mole. Very good. Okay, now what do we... Don't worry, we didn't forget the last one. Oh, there's 2 more. Oh, we almost forgot. Okay, we got this C to O bond. Looks like there's only one. Let's do that. So 1 C to O, which is equal to 358. Well, this is exhilarating stuff going through. you can probably fast. I probably sound a lot better if I'm on 2 times speed. So, yep. So 1 CO, and we also have an OH bond. We don't want to forget that one. So that is 1 OH, which is equal to 463 kilojoules per mole. Now, have we done all the bonds that is in the ethanol molecule? I think we're pretty happy. I'm liking it. Let's just add them up. So we have 348 here, plus your 2065, plus your 358, plus 463. So that overall for ethanol, should just write ethanol just so we know what we're talking about, is 3234 kilojoules per mole. Incredible, but what else is a bond that's broken? The oxygen here. Yes it is. Do we know that? No, we don't. So that's the thing we need to work out. Okay, that's fine. We can just leave that as 3 because we have a mole ratio of 3. Remember, not to forget the mole ratios. Okay. And in oxygen, it's just a O double bond O. So we have 3 lots of that O double bond O. So 3 lots of O double... Oh, that's an O, I promise. O double bond O. Okay. So for the total broken bonds is... Let's go... Broken is your ethanol, which is here, plus what we're going to find out. 3 O double bond O's. Okay. Now we've run out of room. Let's get some more room. The powers of an iPad. Meow. Okay. Wow, I'm back. Crazy. We managed to get some more room. Look at that. Okay, we just moved this stuff down. But the things we worked out are still here. We have the overall equation. Yes. We have the bonds formed. We worked out that was 5998 kilojoules per mole. And the bonds broken, we worked out was ethanol, 3234 kilojoules per mole, plus 3 molar ratios of your oxygen, O double bond O. Beautiful. So now we've worked out that, we can plug it into the equation and get an answer. So this equation up here, let's put the numbers in. Delta RH, what is that? It's given to us at the top right here. Negative 1370. So let's go negative 1370 kilojoules per mole is equal to the sum of the bonds broken. We worked that one out already. Perfect. Bonds broken is 3234. That's a 4, I promise. Oh gosh. Again, you're dealing with my horrific handwriting. Per mole plus your 3 lots of oxygen. That, and then you can go minus the bonds formed, which is 5998 kilojoules per mole. Okay, cool. So now we've put the numbers in that we've worked out. How are we going to work out this oxygen bond here? Well, we need to use math and algebra. Ooh, scary. I'm terrified, but I believe in you. You can do it. What are we going to do? We need to get this oxygen value over to one side of the equation and the numbers over to the other side. Okay, perfect. There's a couple ways you can do this, but like let's just do it this way. So we can keep this number. We're going to just forget units just while we're working it out. I know I'm contradicting what I said, but you know, we're running out of space on the line. So we got a negative 1370 on that side, and let's take the numbers, which is here, and we can just add those together. Well, minus them. So you've got 3, 2, 3, 4, and minus 5998. That comes to a total of negative 2764. So it's the numbers, and you've still got the 3 O double bond O's. Very good. And now what we can do is get the numbers over on to this side over here. So we can go plus 2764 onto both sides. Okay, so if we start off with negative 1370 and you plus 2764, this side it becomes 1394. Put units back in, don't worry, they're back. Is equal to, and if we plus 2764 onto the right side of the equation, it's going to be 0. So that we can just get rid of this. And we have 3 O double bond O's. That's also a 3, I promise. This is great. This is really coming together. So now we've got down to 3 O double bond O is equal to that. So let's just divide everything by 3, both sides by 3. We can do that. So take 1394, divide number 3, okay, and you get 4.6. Okay, reoccurring. So we'll keep the number in our calculator just in case what we need to do. What are we going to do next? We're going to find out. Equals, and that is just the O double bond O. So we're trying to calculate the average bond energy. I think we've done it, so this is great. So let's go. The average bond energy for the that's how you write O double bond O and oxygen gas is, and let's round it to a reasonable number. What is the reasonable number? 3 significant figures. Yes, it is. We love that. 4, 6, 5. Put the units, kilojoules per mole. Amazing. So proud of us. What a great answer. We went through it, we put numbers in, and we got an answer, and now we know the bond energy of the O double bond O bond. Incredible, great work. This is a excellence question, I think. It's giving excellence. So, yay. Nice. Super simple. All you need to know is this equation, plug numbers in, and then boom. Do a little bit of algebra, and then you have a number. Great. Okay, time to move on. Okay, cool. Question B. So, the products of the combustion of ethanol are carbon dioxide, CO2, yes, and water. Wow, very cool. Carbon dioxide contains carbon and oxygen atoms. Yes, it does. Right here. Very cool. Oxygen is more electronegative than carbon. That's a fun fact. Thank you for that. Okay. Makes sense. Draw 2 arrows or add the delta plus and delta minus symbols onto the carbon dioxide molecule shown below to represent the bond dipoles present in the carbon dioxide molecule. And here it is right here. Okay, well, let's do that. Let's do both, just for fun. So we'll start with the delta plus and minus. We are given that oxygen is more electronegative than carbon. Therefore, oxygen is going to have a slightly more negative charge, because electrons are negative, electronegative, little delta minus, boom, over the oxygen, and therefore, comparatively, carbon is going to be delta plus, slightly partially positive. Yeah, that's that. That looks great. So the delta sign is just a partial positive or negative charge. We can put the arrows in as well. So the arrows point towards the more electronegative side. Little arrow going that way. And that bond. And the other. That arrow goes that way. Amazing. So you only need to do one of them. You can do your favorite one. I'm more leaning towards the delta plus and minus. That's more of a vibe. No reason, just for fun. Cool. Okay, that looks great. Pretty simple so far. So we need to now circle the word that describes the polarity of each molecule. So CO2, which we just looked at here, is it polar or non-polar? And then also water. So it's sort of like asking for us to work out an answer and then circle something. So we're gonna circle it and then we're gonna explain the answer. So we know that carbon dioxide is a non-polar. Yes, it is. Okay, and we're gonna go through that. And then water, what is that? Well, that is polar. Very cool. So now we can compare and contrast factors that influence the polarity of these two molecules. Perfect. Oh, I got a little diagram. Get excited. Diagram time. Okay, this just looks like a colorful bean. What am I doing? This is apparently carbon dioxide. The red is more electronegative, more negative, and the blue is more positive. So this is sort of what you're looking at in this diagram here, but like with computer things and looking at it. Something like that. So yeah, that tracks. This is positive slightly, and this slightly negative on that side. And now it looks like a bean. Okay, that was fun. Let's answer the question. Bean, get out of here. Okay, bye. Cool. So, compare and contrast. Should we cover one at a time just so it makes sense and then we can put something afterwards? Let's do that. So, let's do CO2 first. Okay, so we know, because they told us earlier that oxygen is more electronegative than carbon. So let's just like make sure that we write sort of that we know that. CO2. Oxygen is more electronegative than carbon. Incredible. Well, you've just restated what they've already given you. Okay. Is more electronegative than carbon. Perfect. So, the C double bond O bond in CO2, you could just do bonds, are polar bonds. That obviously makes sense because there's a difference in electronegativity between the carbon and the oxygen. So it's one side's going to be slightly more negative and one side's going to be slightly more positive. So they're polar. Perfect. So you could even say, just to be doubly sure they know what you're talking about, so the CO bond O's and CO2 are polar bonds as there is an electronegativity difference between C and O atoms. Okay, very cool. Now, we look at carbon dioxide and we have a look at the shape. It looks pretty linear to me. You could go through and like do the shape things and think about what it is, but I mean, it looks linear to me. So let's just write CO2. I mean, you probably should know that CO2 is just linear. It's a good thing to know. You could work it out if you want. Is a linear molecule. Perfect. So, now let's have a look at the bond dipoles. Let's say. So, the bond dipoles are, how are they arranged? Let's have a look. We've drawn them down here. one is going left and one is going right, and they're both the same bond. So they're both kind of pulling away exactly the same, very symmetrical, right? So the bond dipoles are arranged symmetrically. Is that how you spell it? I doubt it, but whatever. I can't spell. The bond dipoles are arranged symmetrically. Yes. Therefore, they cancel out. Yes, one pulls left, one pulls right, the same amount cancels out. Therefore, they cancel out. So, overall, CO2 is non-polar. I like it. So there's no overall molecular dipole because the individual bond dipoles are cancelled out because of the symmetry. Beautiful. Now, should we do water? H2O. I got a diagram for water too if you want to see. It's very cool. Okay, you can bean, get out of here. Okay, cool. Water, what do we got? H, you can see that under there. O, H, very good, that's that. Again, we have the delta plus, which is the blue, and the delta minus, which is the red. Makes sense. Oxygen is more electronegative than hydrogen, so the electrons, I go that way. Kind of gives away that this is going to be polar, but let's go through the answer and figure it out. Okay, by diagram. Nice knowing you. Go join the bean. Okay, cool. So, H2O. Again, do they tell us that oxygen is more electronegative than hydrogen? No. Something you just have to know. You could just look on the periodic table, which they give you, right? So generally, the periodic table, like everything goes, trends in electronegativity go towards fluorine. That's a general rule. They go from less electronegative over here and here and here, and they get more electronegative going this way and this way. So if where's hydrogen just chills over here, right? So we can say that hydrogen is less electronegative than where's oxygen? It's like here, right? Is it right next to fluorine? You're given a periodic table. You don't need to figure this out. But yes, so oxygen is more electronegative than hydrogen. Makes sense. Okay, so let's write that. Not me forgetting how to spell oxygen. Oxygen is more electronegative than hydrogen. Okay, cool. And we can sort of follow the same vibe that we did for CO2. So the OH bonds in water are polar bonds, as there is an electronegativity. I did not say that up here. Is there a electronegativity difference between O and H atoms? Okay, yep. Is my writing legible? Not really, but whatever. I'm speaking at the same time, so maybe you could figure it out. Cool, so we've said there's an electronegativity difference. Now, let's have a look at the shape of water. Not given to us, so we need to sort of either know it or work it out. Oh, no, jokes. Big jokes. They gave it to us. Wow, they're so kind. There she is. Hey, water. Wow, it's looking bent, right? Because we worked that out in question 1. So we know that H2O is bent. You could do the working out to get there, but let's just say we know it's bent. Looks pretty bent to me. So H2O is bent geometry. Perfect. And then, so what we can say now is the bond dipoles are not, exciting, are not arranged symmetrically. Or you could say they're arranged asymmetrically. The same thing. Let's just make sure they see that. Yep, okay. They're not arranged symmetrically. Therefore, they don't cancel out. No way. So there is an overall. Yep, that's not how you speak. So water is an overall polar molecule. Makes sense. Bond dipoles, they're not cancelling. No, because like which way are they pointing? Let's have a look. That way, and then like that way. So like they're kind of all coming up. A general vibe of upwards. So there's like a molecular dipole across the whole molecule. Yes, there is. So it's looking pretty polar to me. So yeah, perfect. It's polar. What do we have to do? Compare and contrast. So you can either write boom, boom, individually and then do a little compare sentence at the end, which is sort of what, I don't know, it makes more sense for explaining. But you could do one paragraph that sort of does both of them together. But let's just put a little compare and contrast. So both CO2 and water have polar bonds. Polar bonds. As the bond dipoles in CO2 are arranged symmetrically, they cancel out, leaving an overall non-polar molecule. As the bond dipoles in CO are arranged symmetrically, they cancel out, leaving an overall non-polar molecule, while in water they are asymmetrically arranged, so polar. Okay, I'm just running out of room, so I'm paraphrasing, but like you could probably do this in one paragraph. I like it. We've done great. It's also giving sort of excellence vibes. A compare, a contrast, two different molecules. We've said they're polar and not polar. Incredible. Well done. I'm loving it. What a fun question. Okay, we're doing great. There's only one more question, and it's question C, and we can get rid of these diagrams. Bye, Bean. Nice knowing you. Okay, final question. Question C. Let's have a look. The combustion of fuels can result in toxic byproducts. Oh no. Such as carbon monoxide. Very scary. Yes, it is. That is, yeah, terrifying. Okay. A catalytic converter can be used to convert these compounds to less harmful substances. Catalytic converters often contain the element palladium. Where are we going with this? Complete the table. I really don't like these tables. I think they're a little bit silly. But NCEA wants to have a little table they can give some achieve marks for, maybe. I don't know. Let's do the table. Carbon monoxide. What is the type of solid? Well, it's quite funny, carbon monoxide. If that's a solid at atmospheric pressure, it's got to be like at negative 205 degrees Celsius or something to be a solid. It's usually a gas, but I guess we don't need to know that. As a solid, it's going to be a molecular. solid. How do we know this? Well, for molecular, generally, if you have a periodic table, I really should get a periodic table. We'll get one ready for the next video. And you've got like, you know, the line that kind of comes across here, separates like the metals from the kind of things that are non-metals over in this situation. If there's elements bonded to each other in this area, such as carbon monoxide, like carbon and oxygen around there, there's probably a nitrogen between them. It doesn't matter. Two things bonded in here, it's going to be molecular. That's sort of the vibe. So it's a molecular solid. What's the type of particle? Molecules. See what I mean? It's a silly table. Okay. Attractive forces. We covered this in the first question. We know that between molecules you have weak intermolecular forces. That holds together the individual molecules of CO. It's this sort of, well, that would not bond. This sort of vibe. The weak intermolecular forces between the CO molecules. Okay, we don't need to know that. Next one, palladium. Now, if you're looking at a periodic table, you'll see that palladium comes under, it's probably sitting around, I don't know, maybe like here or something. Hey girl, hope you're having a great time. It's a metal. It's in the metal area. It's just by itself. Nothing else like bonded to it. It'll be metallic. Cool. What type of solid is it? It's a metallic solid. The type of particle? Boy, can't you wait? What's it gonna be? Metal atoms. Wow. Okay. I don't know. It seems silly, this table. Okay. I'll stop being mean to the table. You could also say here. You could say metal cations in a sea of delocalized electrons. You could say that, but metal atoms are fine as well. What are the forces holding it together? Metallic bonding. It's just silly. You're repeating yourself. And what is this teaching you? Okay, like I'll leave the table alone. We're done with the table now. Table complete. Let's actually answer the question and learn some chemistry. When exposed to exhaust gases greater than 300 degrees Celsius, palladium remains in its solid state. Okay, makes sense. It's a metal. Just a little bit hotter of a metal, but it's still a solid. Okay. Use your knowledge, structure, and bonding to explain the high melting point of palladium. Okay. A bit of a confusing question because they trick you into thinking it's going to be about CO and like a catalytic converter, but no, it's not about that at all. That was just for the table. Tables. Just explain that about palladium. So this is only actually a merit question. No compare and contrast sort of things. So pretty simple. I believe in us. We can do it. So what's going on in palladium? So we know that, as we said before, palladium is a metallic solid because, you know, it's in the metal area of the periodic table. Perfect. Now, what's actually going on inside? It is made up of metal cations, positively charged cations, as opposed to anions, which are negative. Yeah, we know that. Not cations. Now that's a fun one. People love to joke about cations. It's not how you say that. It's not. It's made up of metal cations arranged in a lattice. Just how they're arranged, evenly spaced out, like 3D sort of lattice. Metal cations arranged in a lattice with a sea of delocalized electrons. It seems a bit silly when you first hear a sea of delocalized electrons. We're not in the ocean. What is this metaphor? Why is it a thing? Maybe I can do an individual video about this specifically. But like, it's saying that it's not just palladium atoms just chilling right next to each other, no charge like this. Apparently not. They're saying it's sort of more like palladium cations. Let's give them a little charge. Okay. So to become positively charged, you need to lose an electron. So the electron that was part of this, he's just out here. He's just chilling. This one from him, this one from him, this one from him. And so they can all like swish around. It's just, they can be shared between the different palladium cations. So that's why they call it a C, because this guy, he can share his electron to him and he can share it back. So there's no specific area that these electrons are in. It's kind of like a delocalized throughout this lattice of palladium cations. So that's why they say it's a C. It's kind of like the ocean. How beautiful. Cool. We've said that. What do we want to say? Made up of metal cations arranged in a lattice with a sea of delocalized electrons. So held together by what we said earlier, metallic bonding. How specific? Yes. Now, metallic bonding, just the general vibe, it sounds pretty strong. So let's say that it's a lot stronger than the weak intermolecular forces. So we can say metallic bonding is strong. Yes, it is. Cool. So if a bond is strong, it's going to take a lot of energy to break it. It makes sense. So it requires, you can just say a lot of, what sort of energy? Well, they're heating it. So let's just say a lot of heat energy. You can go, okay, cool. So it requires a lot of heat energy to break them. Perfect. So you can just say, therefore, if it takes a lot of heat energy to break them, therefore, palladium has a high melting point. Structure and bonding to explain the high melting point. You've explained. It's a metallic solid. You've got metal cations arranged in a lattice with a sea of delocalized electrons between them. They're held together by metallic bonding. Now, metallic bonding is strong, so it requires a lot of heat energy to break them. Therefore, palladium has a high melting point because, there's not enough energy that's coming from the 300 degrees to break those bonds. Do you want to say anything more specific? High melting point, you could say, so at 300 degrees Celsius, it is still a solid. Beautiful. Merit. Very, very good. Merit question. Tick. Like it. Incredible. I'm so proud of us. We did it. Now, what's next? Yep, that's all of question 2. A little bit confusing how they put the merit one at the end. Oh, wow, caught me off guard. But yeah, I'm happy. We did great. We covered those. Question 2, I'm gonna say it was very good. Tick and a smiley face. I'll give us an E8 for it. Beautiful. I hope everyone enjoyed. We can go through the final and third question maybe in the next video. How exciting. So stay tuned and I hope you enjoyed. Okay, bye.